Okay, so we are looking at two different tests that took place, and we can assume that everything was the same, except that in one case, the one student was doing a two-tailed test right here with p does not equal 0.85, and the alternative hypothesis, which is, a one-tailed test. So keep in mind, don't do it. So keep in mind that because the p-value for a two-tailed test is 2 times the p-value that we calculate, so we have to do this, that means that we can really only afford a 2.5, a 0.025 probability on either tail, because it has to add up to 0.05. So basically the p-value that we calculate, we double it, and so we can only have a p-value of 0.025 at most. All right, so anything that is, so if this is my like 0.025 level right here, and I have a corresponding 0.025 level down below, anything that falls in one of those two regions is just fine for a two-tailed test. But anything that falls in this middle region in any way, shape, or form would not be significant, okay? So let me get rid of those. Now with a one-tailed test, we're taking that entire 5% area underneath the tail and putting it all under one tail. So now there's this kind of region. In fact, I'm going to draw this a little differently. I'm going to draw it on this side because we'll see why in a second. But basically, I've got this region right here under one tail, which represents 0.05. So I'm going to zoom in on this part of it, just this lower tail. So I can have my critical value right here, where my where 0.05 lives, and the critical value for that 0.05, if you go to your Z table, is 1.645. And actually, at this point, it would be a negative 1.645. Now, the critical value at this 0.025 level is the 1.96, negative 1.96. So I'm really looking for a Z statistic that falls in this range right here, where, just to clarify, I'll undo that and try it over again. In this range right here, where, to clarify, this would be a Z statistic. Any Z statistic that falls in here would be significant for a one-tailed test, but would not be significant for a two-tailed test. And again, hopefully we've gone through the logical reasoning chain there to make sure that makes sense for you. So I know it's going to be in the only one number that falls in that range is this number and 1.8. So now it's just, is it positive or negative? I set it up as negative on purpose because that is the answer, but we need to think about why that would be the case. If our alternative hypothesis right here for the one-tailed test is that our true population is less than the predicted point, or the assumed 0.85, then we're looking for a difference that's going to end up on the left side of that. So we are looking at negative Z statistics, so that helps us understand it needs to be that value, not this one. Okay, again, that might have been some difficult reasoning to try and think through, but hopefully it was clear enough. There's a narrow range between your two critical values that makes it significant for a one-tailed test, but not significant for a two-tailed test. So we are looking at the chi-square test for homogeneity. Luckily, I'll just preface today's class by saying most of the stuff that we learned today is going to transfer directly to tomorrow when we look at the chi-square test for independence. So a lot of this is going to just be a straight transfer. The chi-square test for homogeneity is used to determine if distributions between two samples on the same variable are the same. Now, it can be two or more samples, I should say that, but we're really, well, let's kind of use an analogy to kind of think through what this test is for. So when we were doing a one sample Z test, and I picked that one for simplicity's sake because proportions are a little bit more straightforward. So if I had a one sample Z test, what I'm basically saying is I found a p hat. how close is that to the predicted P that I might have gotten from some national statistics, or just it's assumed to be true based on some kind of theory. So I'm comparing this value that I found from one sample to a value that was given to me that is assumed to be true. Okay, so there, and that would be, of course, comparing it to our null hypothesis. So that's a one sample z-test, and that's going to be kind of like what we did yesterday. Now, a little bit different because we were looking at a distribution of multiple categorical or multiple categories, one categorical variable, but multiple categories. So I basically took yesterday, I said, here are all my categories, and I'll just pretend like there's a table with these represent the values in it. And this is almost like my p hat. Now, don't get too caught up on that notation. But if I pretend like all this sample and the category breakdown that I got was like my p hat, I was comparing it to an assumed proportion, which would have had these assumed counts and the expected counts. So it's really kind of a similar, by way of analogy, a similar type of test going on. One sample given, one variable that we took data on, and it was just one variable yesterday. We looked at car color. That's one variable. We just happen to have 9 or 8 categories, whatever it was, 8 categories. So now, today what we're doing is going to be kind of the analog for the 2 sample z-test, where in a 2 sample z-test, I have p hat sub 1 and p hat sub 2. There's no assumed value that I'm comparing it to. I'm just comparing these two, and my, of course, null hypothesis is that there's no difference between them. But there's no sort of standard that I'm holding these two proportions up against. I'm just comparing them to each other. All right, so if that makes sense, when we're looking at a chi-square test for homogeneity, we're saying here's 2 distributions. All right. So these 2 distributions, are these 2 distributions similar to each other? I don't know what it should be in like a universal distribution of this, but I do know that I've got a distribution here of, that might look like this. And I'm going to compare it to this distribution right here. Are these 2, thing that keeps happening. Are these 2 distributions equal to each other? All right, so if that kind of follows and you're able to understand that logic that we just ran through, we're just comparing 2 samples. Now we do have to change up our calculations a little bit, and this is the definition from the textbook. I'm not going to read it, except to say right here that it tells you that it's 2 or more groups on the same categorical variable. All right, so one of the hardest things with chi-square is going to be distinguishing when we should use test for homogeneity, test for independence, those 2 especially. But then sometimes you're going to wonder, should it be the goodness of fit? But goodness of fit is just one sample. And anyways, the other thing in this definition that's really good, and we're going to come back to this, so we don't need to talk about it now, is how we find our degrees of freedom. And in fact, I won't talk about it anymore right now, but that's the definition from your textbook. And I think it's good to kind of go back and reread some definitions until you really get the idea down of what the chi-square test, what they all mean. Now, here's one thing that I wanted to point out, because this is, I didn't catch this when I first put up the reference posters, but I made a change. And so the new reference posters I uploaded today, and there's only one change to it, but notice it has this change added to it. So when you have 2 or more samples compared on one variable, that's going to be a test for homogeneity. So these 2 labels right here should be switched. And we'll talk about independence tomorrow. But just keep that in mind. And notice right here for your, this is your calculator command. So we're going to talk today. Luckily, you can see we're using the same test for both of these, which is why whatever we learn today will basically be the exact same thing for tomorrow. But on your calculator, you use the goodness of fit test for your goodness of fit. Okay, that makes sense. All right, enough about that. If you go and re-download the reference posters, if you already had them, you can delete the old ones. re-download the new one and it'll have that correction made. Okay, so we're gonna run through 2 chi-square tests for homogeneity today. One of them I'm just gonna kind of run through, talk about the differences between this and what we did yesterday. And then we're gonna go through another one where we make it more formal, what a formal answer should look like. Okay, so luckily hypotheses for chi-square, all of the hypotheses are pretty straightforward. And we already kind of made the point that all we're doing is we're looking at 2 distributions and seeing if they're the same or not. So our null and alternative hypothesis, really without even reading the prompt for this, if I know it's a test for homogeneity, then my 2 hypotheses are going to be the distributions. So the distributions are not different. And then the alternative would be the distributions are different. So now we can add some context. So I'll kind of read this. Right, so Abby and Mia are trying to figure out if the gender of an interviewer could affect the responses to a survey question. So they got 100 males from their school. Half the males were randomly assigned to be asked, would you vote for a female president by a female interviewer? The other half of males were asked the same question by a male interviewer. The table shows the results. Okay, so if I wanted to change my null and alternative hypothesis in any way, I could say the distributions of males responses to questions based on a male interviewer versus responses to questions versus assuming with a female interviewer, I can't talk, are not different. So we just can add it in the context about what the specific problem is, but generally speaking, this is what they are. These are the hypotheses, and you can see that right here. Again, this is in the reference posters. You can see your homogeneity, no difference in distributions. Alternative is there is a difference in distributions, and it's that straightforward. Okay. This is something new, and we're going to see this calculation twice today. So hopefully it's really pretty straightforward. But when we were figuring out expected counts yesterday, all we had was we had a breakdown of, and I'm going to bring up yesterday's problem, just so it's 18%, 16%, and then dot, dot, dot. There were more, so it doesn't matter. Then there was a total of 300. So we're trying to figure out what's our expected count. Oh, we just take the sample size and multiply it by each percent. Now, we don't know what the percent is necessarily. We can't just do a quick calculation like that for expected value because we're dealing with two-way tables, and that's going to be one of the key characteristics. In fact, that's going to be a major sort of just sign to look for in the problem. If you're given a two-way table, you should automatically be thinking it's either homogeneity or independence, chi-square test. All right, so we are dealing with a two-way table, and so you have to do a different calculation to figure out expected counts. And what we do is, if I want to know how many males would be expected to answer yes with a male interviewer, then I need to take the row total, which is 69, multiplied by the column total, and then divided by the table total. So it sounds weird at first, but I've got the row, so I'm just going to put row for short, but row total times the column total divided by the table total. All right, so we can do this, and so if I do this first one, the row total is 69, the column total is 50, divided by 100, which is the table total, and this turns out to be 34.5. So when we get to the next example, you know, the numbers are a little weirder and you end up with strange decimals. But in this case, it works out not too bad of a problem. So I would expect 34.5 males to answer yes when a male asks the question, assuming there's no difference between the lists, and in between the distributions, I should say. So the next one, I want to figure out, what about males saying yes when a female asks? So I need to find the row and column totals, multiply those together. This example is a little bit easier because the column totals are both the same. They're both 50. So when I get the answer to one of these, I get the answer to both. All right, so 69 times 50 divided by 100 is still going to be 34.5. And this makes sense because if these two distributions are the same and we have the same sample size in each, then I would expect the same breakdown for yeses, nos, and maybes. All right, so now I'll just keep going through at this point a little faster. So now I can say, for this, it's going to be 11 times 50, which is, I'll just write it out, 11 times 50 divided by 100 is 5.5. So, of course, that's the same right here because 50, 11, and 100 are still the same numbers. All right, so 5.5. All right, and now for the last row values, it's going to be, for this, it's going to be 20 times 50 divided by 100, which is going to be 10. All right, so 10 and 10 right here. These are my expected counts. We do need to calculate these by hand. There's not a convenient way to get this on the calculator. So you could potentially do some matrix operations and stuff like that. So, but we're not going to be worried about it. It's easy enough to do it by hand. All right. So there we go. I cleared that away. Hopefully I'll unclear it. All right, so if you still needed to look at that, I'll leave it up. But you can see this from your reference table. Luckily, like I said, everything you're learning today can be directly applied to tomorrow with a couple of exceptions. So when you're looking at a two-way table, you're going to have to do row times column total divided by table total. Okay. So now we want to calculate the value of the chi-square statistic. And we've got this expected counts. We know the observed counts, and we're going to have to do some math. Now, of course, we're going to have our calculator do it in the long run. But to get started, I wanted to run through the chi-square statistic so that we can see kind of what is going on. So I set up another table. I'm going to do this one, and we'll do it somewhat quickly because we already saw the overall breakdown of how we do this. Okay, so on this table, I've got, here are the different cells that are on the two-way table. So it could be a male interviewer, and the answer is yes. And of course, that corresponds to this right here. So I'm just going to start filling it in. So yes and male is 30. Let me get rid of this stuff. All right. Yes and female is 39. No and male is 8. No and female is 3. Maybe and male is 12, and maybe and female is 8. The expected, I copied those down right here, so I can just put those in 34.5, 34.5, 5.5, and the same, and then 10 and 10. All right. So observed minus expected, we're going to see a nice thing come about as we do this. We get the same number twice, just different signs. So I'm going to get 4.5 for both of these, negative 4.5, of course. Now I'll get 2.5 and negative 2.5. And I'm going to get 2 and negative 2. Square this, and I'm going to get 20.25. both times, 6.25 both times, because the squares or the negatives cancel out. It's 25. And this will be 4 both times. Now I want to divide. I don't know these numbers, so everything is the same for each pair. So I'm going to get 0.587, and these are the contributions that each cell contributes toward the chi-square statistic. So I'm going to have 0.587 added from the first two. And then when I get to the next one, that's 6.25 divided by 5.5. I get 1.136. And so 4 divided by 10 is just going to be 0.4. So these are all the contributions for all 6 cells that make up our two-way table. And I'll say this now, and this is going to be important later. These are the cells that we are concerned with. We use the marginal distributions when we're figuring out our expected value. But now for the rest of this, we don't care about those numbers. So we want to focus only on the observed counts and expected counts. That's going to be important when we go to the calculator later, okay? So now I can add this up. And I know I'm doing this calculation quickly, but we're not going to be doing it by hand. So as long as you're following along with the concept, then that's good enough. You don't need to be able to do this calculation over and over and over again. So I got 4.246. And that's our chi-square calculation, or our chi-square statistic. All right. And that is the long way of doing it. This one doesn't take too long. It actually isn't. This one doesn't take that much longer than doing it on the calculator. But of course, we can edit on the calculator pretty darn quickly. So the next thing I want to do before we move on and interpret our chi-square, I wanted to show you how you actually do this on the calculator. Okay. So I will delete this unless there are any questions. Okay, we're going to need to set up matrices. So you should have worked with this in the past, and hopefully, I mean, even if you didn't, it's really not that complicated, but we're dealing with a two-way table. And remember, oops, what just happened? What did I do? I don't know what I did. Let me just, anyways, I think it's all back to normal. Our two-way table is a matrix, and I'm comparing it to another matrix. So I want to set those up. So, and of course, if it was a real matrix, we might do it like this with, 6 values right here. So we're not worried about matrix notation so much. All right, so this should be refresher for all of you. You want to hit second and then your inverse function button right there, and that will be take you to your matrices. You got a bunch of matrices, but what I highly suggest is that you only ever work with A and B, and we will, by way of protocol here, just always use A for the observed counts and B for the expected counts. So if you scroll over to the right when you're in your matrix menu, you can get to edit, and you want to go to matrix A, edit that one first. We're going to have it's rows by columns. So we're going to have 3 rows by 2 columns. So a 3 by 2 matrix. And we can just plug in these values. Now we don't have the values right away, but here, I'll just kind of show this. We don't include the marginal distribution. We're only worried about the counts, the observed counts for each cell. All right, so we'll edit A and B. B will be expected. So let me actually go back a previous slide so you can see all these counts right here. You can plug them in. now that we've got the matrices edited, we've done the hard part. Now we just need to run the chi-square test. And so you hit stat on your main menu, you do stats, tests, and just next to the test we did yesterday is your chi-square test. And notice that it's already pre-filled with matrix A is your observed and matrix B is your expected. So if you edited it the way that I suggested, you don't need to make any changes here. Just calculate, and it gives us our answer. And we can see that we calculated a chi-square of 4.246 when we did it by hand, and that's pretty spot on with what the calculator gave us. So that's just a way of confirming that now we are doing it, we're plugging numbers in the calculator correctly. Okay. So pretty straightforward, but you will have to navigate to matrices. So having said that, it also tells us, of course, the p-value and our degrees of freedom. And we'll talk about degrees of freedom in just a second, but this is going to be something that's kind of interesting / somewhat important. So I mentioned at one point yesterday or whenever that the chi-square distribution skews right. And when you look in your AP formula sheet, it shows you just one example of a chi-square distribution. But notice just how vastly these change. So if you have 1 degree of freedom, it looks kind of like a power distribution. If you've got degree of freedom 2, it kind of looks the same. Degree of freedom 3, and that now it looks just in the smallest possible way, it looks like a somewhat normal distribution that's highly skewed. So a skewed distribution. And anyways, it gets more and more normal the higher your degrees of freedom get. And then this looks like a real normal distribution if you get up to really high degrees of freedom, talking about like 1,000 degrees of freedom. But even at 10 degrees of freedom, you can see there's a strong right skew to it. So anyways, it's good to kind of visually see how this changes with degrees of freedom. All right, so we've got our chi-square statistic of 4.24. Really, if I rounded, it'd be 4.247 from the calculator. And I guess we're not really doing anything on the previous slide. But what I wanted, the calculator gives this to me automatically, but it is important to understand how the degrees of freedom are calculated. And maybe I'll go back to the previous page. Well, you can see it's number of rows minus 1 times number of columns minus 1. And this actually relates to, it's kind of a 2-dimensional version of what we did yesterday. So when we're doing our goodness of fit, we have basically 1 dimension, a linear dimension with, here I've got 1, 2, 3, 4, 5, 6 categories. So we just ignore this one, and I've got 5 degrees of freedom. That was pretty straightforward. Well, now what we've got is basically 2-dimensional distributions like this. And now what I'm going to do is I'm going to pretend that I've got, let's just go with this, a 2-way table that might have this many cells in it. All right. Now, of these, I can do this 6 minus 1, because it would be 6 columns, and now I've got 4 rows, but minus 1 gives me 3 right here. So if I ignore this last row and this last column, and I take those individual degrees of freedom and multiply them together, that's how I end up with, it looks like 15 degrees of freedom for this problem. Okay, so hopefully you can kind of see the analogy or the sort of connection, how these are related. So these look very different on the next page for our degrees of freedom, where we've got just number of categories minus 1, and now we're multiplying 2 things together to get degrees of freedom, but it's really related. This is kind of a 1-dimensional and now 2-dimensional. We got length, if you want to put it into geometric terms, and area. Okay, so that's probably good enough to get the idea across. So the calculator did this for us automatically. You can see it's pulled up already, and it showed 2. Of course, think back to what we had. We had a 3 by 2. So we just had 2 minus 1 right here, and then 3 minus 1 was 2. So basically we had 2 cells that were degrees of freedom. Okay, and that will of course determine which chi-square distribution we are working with, which is why I showed you how drastically they change. Our conditions haven't really changed. Independent, random, independent, and normal. Straightforward. So having gone through kind of the overview of the chi-square test for homogeneity, let's go ahead and do this more in a formal way. Okay, a survey of articles from the New England Journal of Medicine classified them according to the principal statistics methods used. The articles recorded were all non-editorial articles appearing during the indicated years. Let's just look at whether these articles use statistics at all. So this is a survey of articles. It's important to point that out. We're not saying these are all of the articles. And the essential question is, has there been a change in the use of statistics through time? But we're going to compare different distributions. And notice that we actually have 3 distributions we're comparing here. Well, I shouldn't include that last one. So I'm comparing 3 different samples, and there we go. My hypothesis, my null hypothesis, is that there is no difference in, I'll put in some context on this one just to be more thorough. There's no difference in use of statistics for these 3 samples. Of course, my alternative would be that there is. I'll be a little bit lazy here. So basically there is a difference. Anyways, so I just rewrite that. My significance level, unless told otherwise, I'll just stick with the standard 0.05. Okay, straightforward with that. Now I can run through and name my procedure, which is going to be my chi-square test for homogeneity. Yeah, something like that. My conditions, random. Well, because it's a survey, I will assume that this is random. And I'm going to assume all of these are random. The 10%. Here's where we just have to assume if we've got 332 and this is a survey, I will assume that for all 3 of these samples, that this was less than 10% of the population. So here's where I might put a statement. I assume that the survey was not more than 10% of the population. Okay, so, I mean, we're at least justifying our own thought process. All right, the last one, normal. Now we can't answer this one until we know the expected counts. And remember that our rule here is that our lowest expected count has to be greater than or equal to 5. So for checking conditions, I'm only going to worry about the lowest one. And this is where it's not too difficult to figure out. For my rows, it looks like my lowest count is going to be in this row because that's the lowest row total. For my columns, it should be here because that's my lowest column total. So my expected count for this is going to be 144 times 115 divided by the table total, which is 758. And that gives me an expected count. The absolute lowest expected count is going to be 21.85. So yes, we meet this condition. All right, and what I might do right now before we move on to the next part is we need to have this. So I'm going to go ahead and lay out all of the expected counts. I know this one is 21.85. I will leave this here and you guys can fill in these cells with expected counts. Good work. We got the table filled in. I will leave that table. I'm going to erase everything else that I wrote here though. If I can. It doesn't want to let me erase part of this. All right. It's really not going to let me erase. I don't know. Something's going on. It won't let me erase chi-square. So we'll just work through that. So our specific formula now is the same as always. It's the sum of, I'll put chi-square right here. And just as a preface for this, again, remember, we're going to go through and figure out this part first, and then we're going to go back and add in the work in the picture. Okay, this is kind of like what we looked at yesterday. So it's going to be the observed minus the expected squared divided by the expected. Okay, and at this point, we can actually kind of work on, we have the observed counts right here. I've got the expected counts right here. So you can set up your matrices. This is going to now change to a 2x3 matrix. And we can run through, let the calculator give us all of our numbers, and then we'll go back and add the work. Okay, so there you go. You're letting your calculator kind of take over and do it. You could have, this 0.000000003, it's totally good. You could, copy down what your calculator is showing, times 10 to the negative sixth. It's, I think it's fine either way. So now what we want to do to show our work, what we were doing is, for the chi-square, I was comparing this expected count to this actual count. And I did that for all 6 cells. And I didn't have to go in any particular order. I could have jumped around and then next compared the 101 to the 93.15. So there's no particular order that we have to go in. But to show my work, I just want to show the first cell and the last cell. And this is all you need to show. So there are 6 cells we did this calculation for, but I'm only going to show the very first and the very last. So my calculation would have been the observed 90 minus the expected 63.07 squared divided by the expected 63.07. And then I would have next done maybe the next cell over, but I'm not going to show that. I'm just going to put ... plus, and the very last cell I would have done is this one. So my observed here is 271 minus, that's 251.92 squared divided by 251.92. And so it's implied that we did the same calculation for all the cells, but we're just showing the first and the last. And we got 25.28. And the p-value is as given. Now we don't need to show that with work. So the picture, we can run this on our calculator. So if you go back to your chi-square test, stat, tests, option C, and run it again, but at the bottom, choose to draw it rather than calculate. And this is where it's kind of good to show that we know that we have a distribution that looks more like this. All right. So you don't want to just put in a generic chi-square. I think it'll be helpful to show that it's a degree of freedom 2. So if you can even do this, chi-square, no, not chi sub 2, chi-squared for 2. That's kind of saying it's a chi-square distribution for 2 degrees of freedom. And I ended up with, it doesn't even show up on my screen, and it doesn't show up on yours, but we could pretend like here's our chi-square value. And then this area underneath is the p-value. So there we go. That's pretty much all there is to it for showing the picture and showing your work. Hopefully you're good with that. And I put this table here just to show you one more time, and I'll clear a little bit of space. All right, so if I looked at the 2 degrees of freedom, because this table is available to you on the test, remember that. So if I look at this row and I come all the way over to the end, my 25.28 is way off the table to the right. So from the table, I can say that my p-value is going to be less than the lowest p-value they show is 0.0005, 0.0005. Remember, your tail probability is the p-value. Okay, so you don't need to work with the table, but I like to make sure that you're comfortable with it. All right, so now all we have is the conclusion. I'm going to clear it. We don't need our calculations anymore. So I'll clear all of this. And our conclusion can now be kind of following our template that we've used many, many times. Because the p-value was less than the significance level. And here's where I can put in the numbers. I don't remember exactly, was it 3.24? I guess I should run it real quick. 3.24 times 10 to the negative 6th is less, is less than 0.05. We reject the null hypothesis. All right, so that doesn't put any context into this. So we want to add another sentence. And I'm going to go back to the question we were asked. Has there been a change in the use of statistics? So I'm going to answer that question directly. There is convincing evidence that there has been change in the use of statistics, and I can even put more context, use of stats in the New England Journal of Medicine over time. Now, if it wanted us in perhaps an investigative task or something else, just a regular FRQ, if it wanted us to comment on what kind of change has happened, well, this is where we could compare it to the expected counts. So, we could look at this in more detail, but my expected counts, just to see it one more time, I'm just going to put the whole number, 269, 22, and 93, 59, and 252. Okay, so I can see that in 1978 and 90, there were more articles with no stats than we would have expected. In 2000, and vicariously, and therefore, more articles with stats. Well, there's also Oh, I'm sorry, I'm going backwards. There were fewer articles with stats than we would have expected. Here's the expected. So now we flash forward in time to 2004, 2005. There are fewer articles without stats than we would have expected. And there are more articles without stats than we would have expected. So you could just compare your observed to expected. Now that we know there's a statistically significant difference, and you could do further analysis if it asked you to. All right. And 1989 was pretty close to being spot on with what they would have predicted. So that's been the change. So you can say more to that. You could say the change has been to include more stats through time, which I guess is an endorsement for taking a statistics class, because you can see it's becoming more and more prevalent. There you go. I'm selling you guys on a class you're already enrolled in. All right. So there we go. There's not much homework. You can see it's only 2 problems. That should be only the odd problems, as you expect. There's not much there, but there's going to be a much bigger homework assignment tomorrow once we have this test in our toolkit as well, because one of the hardest things is distinguishing between the 3 chi-square tests and when is it appropriate to use each one. So your homework tomorrow will take that into account also. But that's all we've got for today. We're out about 30 minutes early. If you've got any questions, stick around. Otherwise, have a wonderful day.